So we're going to start with igneous rocks, and igneous rocks are rocks that came from a molten. Molten can either be a magma or a lava, and then the magma cools, and it either cools quickly or slowly, depending on magma or lava, and a process occurs called crystallization, and eventually the rock turns to a rock is simply a solid mixture of minerals. It can occur, or it has to occur naturally as part of our planet, and it can be either organic or inorganic. Molten is either magma or lava. If magma is down inside the ground, typically it has a lot more gases inside because it's not exposed to the atmosphere, so it can't get rid of them. If the molten comes outside, it's called lava, and lava typically has less gases because once it hits the atmosphere, gases are escaped. Igneous rocks are really important because a large part of the Earth's crust is made up of igneous rocks. The Earth's mantle is essentially just one big igneous rock. There's a lot of minerals that are important economically, and some of those minerals are actually found in igneous rocks. When we talk about lava is a lava extrusion, and because of that, any single time that we have minerals rocks that actually form from a lava, we call those rocks extrusive, and we also call them volcanic. If we have rocks that form from a magma, or what we call a magma intrusion, they actually can be referred to as being intrusive or plutonic. The word plutonic comes from the fact that a magma chamber can actually be called a pluton. What you're actually seeing here in this rock is a magma chamber down inside the ground. Typically, I like to think of magma chambers shaped more like this and not so much as an oval. That magma would cool really slowly, crystallization would occur, and eventually it would be a rock filled full of big crystals. And that is essentially what happened in this case. However, if you were to look at the diagram down here in the ground, the rock above the magma chamber got weathered and eroded away, and the magma chamber actually became a hill or a mountain that's exposed on the surface. And you can see an example of this in Yosemite National Park, which is in California. So what you're actually looking at in this graphic is a solid rock, which is basically an ancient pluton or a magma chamber that was once buried far down inside. In this particular graphic, you're looking at magma, and the magma is cooling, and as it cools, you get crystallization, and we can see some really big crystals here forming. What we don't know is the rest of the magma, is it going to continue to also cool slowly, and as a result, the rest of the magma turn into large crystals as well, or will the volcano erupt and the magma come out as lava, which will cool quicker, and the crystals therefore would be smaller. We don't really know that, but it's just a graphic to kind of show you what crystallization looks like in a. So here we're going to look at some textures now, and this particular texture of an igneous rock that you're actually seeing here is phaneritic, which we call coarse grain. So a phaneritic texture or a coarse grain texture, we know that because we can see these crystals here with our naked eye. They're big enough to see, so we know they're big crystals. We know they cooled slowly from a magma. One of the relationships that's really important for you guys to understand is that cooling affects the crystal size. So if you get slow cooling from a magma, then you're going to get large crystals. If you get fast cooling from a lava, then you're going to get small crystals. If the cooling is like instantaneous, and in geological time that would be like, within 20 to 30 minutes, it's possible that crystals would have no time to grow, and as a result, there actually wouldn't be any. So this is the porphyritic, where the volcano cools slowly down, the magma cools slowly down inside the ground and then comes out as lava, which cools quicker. So you get two different sizes of crystals, two different stages of cooling. You have your glassy, your frothy glass, and your compact glass, which I just talked about. That applies to obsidian, scoria, and pumice. Then we have our phaneritic, which is our coarse grain texture. And that's the slow cooling from a magma, all big crystals. And then your aphanitic or your fine grained, which is fast cooling from a lava, all small crystals. In this diagram, you actually get to see a picture of a porphyritic texture, the two-stage cooling. So you can see a really, really large phenocryst, these pink crystals, and then that's surrounded by all small crystals, which is ground mass. And this is how you would actually draw that in a diagram. Here we're seeing an aphanitic texture, which is a fine-grained texture. So here in the rock, all the crystals are there. They're just really small. You can't see them with your eyes. So that would indicate fast cooling from a lava. And we have to draw in something, because if you don't draw anything, it looks like there are no crystals. There are crystals in this particular case. They're just really small. So we're going to take our pencil and just shade in the block. And for phaneritic texture, here's what you would draw. So all large crystals due to the slow cooling from the magma. And this is an example of a rock called granite that cooled slowly from the magma. And as you can see the crystals with your naked. So these are all the rocks. So if you were to remember the chart that we did on the board in class, we had rocks that formed from a magma. We had ultra dark, mafic, intermediate, and felsic. So they all cooled slowly from a magma, so they would all be coarse-grained texture or phaneretic texture. Komatiite, basalt, andesite, and rhyolite, they all cooled quickly from a lava. So because of that, they all have small crystals due to the fast cooling, and the texture would be fine-grained, which we would call aphanetic. We talked about glassy. Obsidian is compact glass, and pumice and scoria are frothy glass, no crystals at all due to instantaneous cooling. And then we also talked about another texture. Actually, we didn't talk about the other texture. It's a texture called vesicular, and vesicular simply means holes. And so how would you get holes in a rock? It would probably be due to gas escape. So as gas gets escaped out of the lava as the rock is being formed, sometimes the holes actually get solidified in place. So I just said the word lava. So a vesicular texture is one that you would typically get with either a glassy texture or a fine-grained texture. So what I'm saying is it's possible for a rock to have a fine-grained aphanetic texture and to also be vesicular, or it's possible for a rock to have a glassy texture but to also be vesicular.